Hello there, and welcome back to the Science Sleepy Minds. Tonight you're standing on the edge of absolute darkness. Picture it. You're 4.5 billion kilometers from the sun, so far away that sunlight takes over 4 hours just to reach you, and when it finally arrives it is barely a pale pinprick, no warmer than a distant flashlight left on a frozen porch. Around you there is nothing but the hum of deep space, and ahead, swelling into view like a bruise on the fabric of the cosmos, is a sphere of impossible blue, Neptune, the 8th planet, the last true planet in our solar system, and you, lucky you, are about to spend the next little while learning everything it has been hiding from us, some of which no one on Earth ever expected to discover. You probably will not survive this entire script awake, and honestly, that is the whole point. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Also, drop a comment and tell me where you're listening from tonight and what your local time is. I always love reading those. Someone is always tuning in from a place I have never heard of, and that makes this feel like a proper global sleepover. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You settle into whatever cozy position you have chosen, and Neptune keeps growing in your mind's eye. That blue. It is not the friendly blue of a tropical ocean or the soft blue of a baby blanket. It is a cold, electric, almost alien blue. The kind of colour that looks like it was invented by something that does not care whether you find it beautiful or not. And the funny thing is, for most of human history nobody even knew this planet existed. Not the ancient Greeks, who mapped 5 wandering stars and called them planets. Not the medieval astronomers who squinted through early telescopes and catalogued everything they could find. Not even William Herschel, who stumbled upon Uranus in 1781 and probably thought he had completed the planetary collection. Neptune was out there the whole time, quietly orbiting, holding its secrets in the freezing dark, and it would take something truly remarkable to drag it into the light. You see, finding Neptune was not like finding the other planets. Mercury, Venus, Mars, Jupiter, Saturn. Those are all visible to the naked eye if you know where to look. Ancient civilizations spotted them thousands of years ago and built entire mythologies around their movements. But Neptune is so far away and so faint that no human eye, no matter how sharp, could ever pick it out of the starfield without help. It sits at an average distance of about 4.5 billion kilometers from the Sun, lurking in a region of the solar system where everything moves slowly and light is scarce. To put that in perspective, if you could drive a car at highway speed toward Neptune, it would take you over 5,000 years to get there. 5,000 years. That is roughly the entire span of recorded human civilization, and you would still be gripping the steering wheel, bleary-eyed, wondering if you had made a terrible mistake. What makes Neptune's discovery story so delicious, and we will get into this properly in just a moment, is that it was not found by someone peering through a telescope on a lucky night. It was found by mathematics. Pure, beautiful, slightly obsessive mathematics. Someone sat down with a quill and a stack of paper and essentially said, "There must be something out there pulling on Uranus, and I am going to calculate exactly where it is." And they were right. Historians still argue whether the British or the French deserve more credit for the discovery, and that argument has been simmering for nearly 2 centuries now, with no sign of cooling down, which is frankly impressive for a dispute about a planet most people forget exists. Here is a quirky little tidbit to tuck under your pillow tonight. Galileo, the great Galileo himself, actually observed Neptune way back in 1612 and again in 1613, more than 200 years before it was officially discovered. He recorded it in his notebooks as a faint star near Jupiter. He even noted that it seemed to have moved slightly between observations, which should have been a screaming clue that it was not a star at all. But he did not follow up. He was busy with other things like revolutionising our understanding of the universe and getting in trouble with the Catholic Church, so Neptune slipped through his fingers. Imagine being that close to discovering a planet and just shrugging it off. It is the 17th century equivalent of having a winning lottery ticket and using it as a bookmark. So tonight, you and I are going to do what Galileo never got around to doing. We're going to pay attention to Neptune. We're going to peel back its icy blue atmosphere layer by layer, meet its strange and doomed moons, walk through storms that make hurricanes look like gentle breezes, and discover things buried deep inside this planet that sound like they belong in a science fiction novel. Diamond rain, superheated oceans that somehow stay liquid, a magnetic field that looks like it was installed by someone who lost the instruction manual, all of it real, all of it waiting for you in the dark. Let your breathing slow down, let your shoulders drop, and let Neptune pull you gently forward into the story. The year is 1821, and you're sitting in a cramped European observatory, surrounded by star charts and the faint smell of ink and candle wax. Uranus, the planet Herschel found 4 decades earlier, is misbehaving. You've been tracking its orbit for years, carefully plotting where it should be based on Newtonian gravity, and the stubborn thing keeps drifting off course. Not by a huge amount, mind you. Just a little nudge here, a slight wobble there, the kind of discrepancy that would be easy to ignore if you were not the sort of person who loses sleep over fractions of an arcsecond. But you are that sort of person, and so are a handful of other astronomers scattered across Europe, and collectively you are all starting to whisper the same thrilling, terrifying idea. Something massive and invisible is out there, tugging on Uranus from the darkness beyond. This is where the story splits into 2 parallel tracks, and depending on which side of the English Channel your loyalties fall, you'll tell it very differently. On the British side, there is John Couch Adams, a young mathematician from Cornwall who is so quietly brilliant that he practically hums with intellectual energy. Adams begins working on the problem in 1843, while still a student at Cambridge. He approaches it with the calm determination of someone solving a particularly satisfying crossword puzzle. If Uranus is being pulled off course, he reasons, then there must be another planet beyond it, and the size, distance, and position of that planet can be reverse engineered from the irregularities in Uranus's orbit. It is, when you think about it, an absolutely audacious idea. He is proposing to find a planet not by looking at the sky, but by looking at equations. Adams works through the calculations and by September 1845 delivers his predicted position for the unknown planet to James Challis, the director of the Cambridge Observatory, and to George Airy, the Astronomer Royal. And here is where the British side of the story turns into a slow-motion tragedy of missed opportunities. Airy is sceptical. Challis is busy. Neither of them rushes to point a telescope at the spot Adams has indicated. The prediction just sits there, gathering dust on desks that really should have been more organised, while across the channel, a Frenchman is about to steal the show. Urbain Le Verrier is everything Adams is not in terms of personality. Where Adams is shy and retiring, Le Verrier is bold, brash, and absolutely certain of his own genius, which, to be fair, is justified because the man is genuinely extraordinary at mathematics. Working independently and with no knowledge of Adams' efforts, Le Verrier tackles the same problem and arrives at a strikingly similar predicted position for the mystery planet. But unlike Adams, Le Verrier does not hand his results to people who will sit on them. He sends his calculations to Johann Galle at the Berlin Observatory with what amounts to a polite but firm instruction. Point your telescope here. You will find a planet. Do it tonight. Galler receives the letter on September 23rd, 1846, and that very evening, with the help of his student Heinrich d'Arrest, he aims the Berlin Observatory's telescope at the coordinates Leverrier specified. Within 30 minutes, they spot a tiny blue-green dot that is not on any existing star chart. It is less than 1 degree away from where Leverrier said it would be. They found Neptune. The feeling in that observatory must have been electric, that particular flavour of human triumph, where the universe confirms that your math was right all along. d'Arrest reportedly turned to Galler and said something along the lines of, "That star is not on the map, and in that moment the solar system officially grew by 1 planet." Now the aftermath is where things get messy. When news of the discovery reaches England, there is an immediate and very British uproar. Adams had the answer first, his supporters argue. He predicted the position months before Leverrier. The fact that nobody in England bothered to actually look through a telescope is a failure of institutions, not of Adams himself. The French, naturally, disagree. Leverrier did the work, published the results, and prompted the observation that confirmed the planet. Priority in science, they insist, goes to the person who completes the chain, from prediction to verification, not the person whose note sat unread in a drawer. Historians still argue whether Adams deserves equal credit or whether Leverrier should be considered the sole discoverer. And this debate has fueled countless academic papers, at least 2 books, and probably more than a few heated dinner conversations at astronomy conferences. The compromise that eventually settled over the scientific community, somewhat grudgingly on both sides, is that both men are credited with the mathematical prediction of Neptune. It is a diplomatic solution, the kind of answer you give when you're tired of fighting and just want to move on, but it papers over a genuinely fascinating question about how science assigns credit and what counts as discovery. Is it the idea or the proof? The prediction or the observation? You can chew on that one as your eyelids get heavier. Here's a detail that tends to get lost in the nationalistic drama. The name Neptune was not the first choice. Several names were proposed in the weeks after the discovery. Gall suggested Janus. Leverrier, with characteristic modesty, wanted to name it Leverrier after himself, which even his supporters found a bit much. The name Neptune, suggested by several astronomers almost simultaneously, eventually won out because it fit the mythological naming convention of the other planets. Neptune, Roman god of the sea. A fitting name, as it turns out, for a world that would later reveal itself to be hiding unimaginable oceans beneath its atmosphere. But nobody knew that yet. In 1846, Neptune was just a faint dot in a telescope, a mathematical victory, a point of national pride, and a profound reminder that the universe is always bigger than you think it is. You lie there considering that. The idea that an entire world can be conjured from numbers on a page, and the thought is both thrilling and oddly soothing. So for nearly a century and a half after that triumphant night in Berlin, Neptune remained essentially a smudge. A tiny, bluish, impossibly distant smudge that even the best telescopes on Earth could barely resolve into anything more than a featureless disk. Astronomers knew it was there. They could track its painfully slow orbit, which takes about 165 Earth years to complete, meaning Neptune has only finished 1 full lap around the Sun since humans discovered it. They could measure its size, roughly 4 times the diameter of Earth, and estimate its mass, about 17 times heavier than our home planet. But the details, the textures, the storms, the secrets, those remained locked away behind billions of kilometers of empty space and the blurring interference of Earth's own atmosphere. You squint at Neptune from your armchair on Earth, and you see almost nothing. It is like trying to read a book through frosted glass from across a football field. That all changed on August 25th, 1989, when a spacecraft the size of a small car, travelling at roughly 60,000 kilometers per hour, came screaming past Neptune's cloud tops after a 12-year journey through the solar system. Voyager 2, the little probe that could, and what it found when it arrived was so unexpected, so spectacularly different from what anyone had predicted, that it essentially rewrote the textbook on ice giants overnight. You need to understand the context of expectations here to appreciate just how shocking Voyager 2's discoveries were. Before the flyby, the general scientific consensus about Neptune was, frankly, boring. Most researchers assumed it would be a quiet, frigid world, a slightly bluer version of Uranus, which Voyager 2 had visited 3 years earlier and found to be remarkably bland. Uranus had presented a nearly featureless atmosphere with very little visible activity, like a pale green billiard ball hanging in space. The thinking was that planets this far from the Sun, receiving so little solar energy, simply did not have enough juice to drive dramatic weather systems or atmospheric dynamics. Neptune, being even farther out, should logically be even more inert. A frozen, sleeping giant. That was the prediction. Neptune, as it turns out, did not read the prediction. When Voyager 2's cameras began returning images during the approach phase, the mission scientists at the Jet Propulsion Laboratory in Pasadena started doing double takes. Instead of a calm, featureless disk, Neptune was alive, raging, swirling, violently alive. Enormous cloud systems streaked across the atmosphere at staggering speeds. Dark vortices the size of entire continents churned in the deep blue. Bright white clouds of methane ice crystals, which the team nicknamed scooters because of how fast they zipped across the field of view, raced along at speeds that made no physical sense for a planet, receiving roughly 900 times less sunlight than Earth. One scientist later described the experience as expecting to walk into a library and instead finding yourself in the middle of a rock concert. Neptune was not sleeping. Neptune was screaming. The flyby itself was a masterpiece of engineering and planning that deserves a moment of quiet appreciation as you lie there tonight. Voyager 2 had been launched in 1977, taking advantage of a rare planetary alignment that occurs roughly once every 175 years, allowing a single spacecraft to visit Jupiter, Saturn, Uranus, and Neptune using gravity assists from each planet to sling itself toward the next. By the time it reached Neptune, the probe was so far from Earth that radio signals travelling at the speed of light took over 4 hours to make the one-way trip. Sending a command and waiting for confirmation was an 8-hour round trip. There was no joystick control, no real-time steering. Every maneuver, every camera angle, every instrument reading had to be pre-programmed with extraordinary precision. The margin for error at Neptune was essentially zero, because there would be no second chance. No other spacecraft was on its way. No other spacecraft has visited Neptune since. Voyager 2's flyby remains, to this day, humanity's only close encounter with the 8th planet, which is a fact that should make you feel both proud and a little melancholy. During its closest approach, Voyager 2 passed within about 4,950 kilometers of Neptune's cloud tops, threading the needle between the planet and its rings with the confidence of a probe that had already done this 3 times before. Over the course of several days, it captured thousands of images, measured atmospheric composition, recorded magnetic field data, mapped temperature profiles, and studied the ring system and moons. The data it sent back would keep scientists busy for decades. And the single most dramatic image, the one that ended up on the covers of newspapers and magazines around the world, was of a colossal storm system in Neptune's southern hemisphere that bore an uncanny resemblance to Jupiter's Great Red Spot. They called it the Great Dark Spot, and it was about to become one of the most intriguing and baffling features ever observed on any planet. Historians still argue whether the initial decision to prioritize Neptune imaging over other instruments was the right call. but looking at what those cameras revealed, it is hard to imagine anyone regretting it. There is a quirky footnote to the Voyager 2 flyby that does not get mentioned often enough. Because Neptune is so far away and the sunlight so dim, the cameras had to use much longer exposure times than they had at Jupiter or Saturn. This meant the spacecraft had to rotate slowly during each exposure to compensate for its own motion, essentially panning the camera to avoid blurring, a technique that had never been attempted before at those speeds and distances. The engineers who figured out how to do this basically invented a new form of space photography on the fly, which is the kind of quiet, unglamorous genius that makes deep space exploration possible. You drift a little deeper into your pillow thinking about those engineers, the ones whose names you will never know, who made sure that when humanity finally got its one and only look at Neptune, the pictures were sharp. The great dark spot stared back at Voyager 2 like a massive, unblinking eye. It sat in Neptune's southern hemisphere, roughly 20 degrees south of the equator, and it was enormous. About 13,000 kilometers long and 6,600 kilometers wide, which means you could have dropped the entire Earth inside it and still had room to rattle around. The spot was dark, oval, and bordered by wispy white clouds of methane ice that clung to its edges like frost on a window pane. It rotated counterclockwise, completing a full spin roughly every 16 days, and it drifted westward across Neptune's face with a kind of slow, menacing purpose that made it look almost alive. Scientists immediately compared it to Jupiter's Great Red Spot, which had been observed for centuries and become one of the most iconic features in the solar system. Here, finally, was Neptune's answer. Its own signature storm, its calling card. But the Great Dark Spot was different from Jupiter's famous vortex in ways that mattered. Jupiter's Great Red Spot is an anticyclone, a high-pressure system that has persisted for at least 350 years and possibly much longer. It is stable, enduring, almost stubbornly permanent, like that one piece of furniture in your grandmother's house that has been in the same corner since before you were born. The assumption, quite naturally, was that Neptune's Great Dark Spot would behave similarly. A giant planet, a giant storm, therefore a long-lived giant storm. It made intuitive sense. The universe, however, has a well-documented habit of not caring about what makes intuitive sense. When the Hubble Space Telescope turned its gaze toward Neptune in 1994, just 5 years after Voyager 2's flyby, the Great Dark Spot was gone. Simply gone. Not faded, not weakened, not migrated to a different latitude. Vanished. The storm that had been large enough to swallow Earth had dissipated entirely, leaving behind nothing but smooth blue atmosphere where it once churned. You can imagine the confusion in the astronomy community. 5 years is nothing in planetary terms. Jupiter's Great Red Spot has been raging since at least the 1600s. Neptune's equivalent had apparently lasted less time than most car loans, but here is where things get even stranger and more fascinating. While the original Great Dark Spot was gone, Hubble found a new dark spot forming in Neptune's northern hemisphere. A completely different storm, in a completely different location, apparently generated by the same mysterious atmospheric processes that had created the first one, and this would become a pattern. Over the following decades, Hubble and later ground-based telescopes equipped with adaptive optics would observe dark spots appearing, persisting for a few years, and then vanishing, only to be replaced by new ones elsewhere on the planet. Neptune, it seemed, was not a world of permanent features like Jupiter. It was a world of constant reinvention, where colossal storms could bloom and die on timescales that were shockingly brief by outer solar system standards. Researchers still argue whether these dark spots are true analogues of Jupiter's Great Red Spot, or something fundamentally different. The leading theory is that they are anticyclonic vortices, similar in basic structure to Jupiter's storm, but existing in an atmospheric environment that is far more dynamic and unstable. Neptune's atmosphere, despite the planet's enormous distance from the Sun, is extraordinarily energetic, and the conditions that sustain a giant vortex on Jupiter may simply not persist long enough on Neptune to keep a storm alive for centuries. It is like comparing a campfire in a sheltered cave to a campfire in a hurricane. Both are fire, but only one is going to last through the night. One particularly quirky detail about the Great Dark Spot that often gets overlooked is the behaviour of those bright white companion clouds. Voyager 2 observed streaks of high-altitude methane cirrus clouds hovering around the edges of the dark spot, and they appeared to be orographically generated, meaning they formed as atmospheric flow was forced upward and over the vortex, much like clouds forming on the windward side of a mountain on Earth. This was remarkable because it implied that the dark spot extended deep into Neptune's atmosphere, acting as a kind of invisible mountain made of spinning air. The storm was not just a surface blemish. It was a towering structure reaching through multiple atmospheric layers, a pillar of organised chaos in an already chaotic environment. There is something oddly poetic about Neptune's disappearing storms, something worth letting wash over you as your breathing slows. Jupiter clings to its storms for centuries, maybe longer. Neptune lets them go, creates them, sustains them for a little while, then dissolves them back into the blue and starts over. Historians still argue whether this tells us something fundamental about the differences between gas giants and ice giants, or whether it is simply a consequence of Neptune's unique atmospheric chemistry and energy budget. Either way, it makes Neptune feel less like a static portrait and more like a living canvas, constantly painting over itself. The spot Voyager 2 photographed so beautifully in 1989 no longer exists, and the storms Hubble sees today will likely be gone within a decade. Nothing on Neptune is permanent except change itself. And if that is not a thought perfectly designed to carry you gently towards sleep, then you are more resilient than most. You let that image settle behind your eyelids, a planet-sized eye, opening and closing in the dark, watching nothing, seen by almost no one, appearing and disappearing on its own ancient schedule. Neptune does not perform for an audience. It simply exists, wild and indifferent, at the edge of everything. The winds hit you first, not literally of course, because if they did, you would not be around to think about it. You would be shredded into particles so fine that even Neptune's atmosphere would not bother noticing. The winds on Neptune are the fastest ever recorded on any planet in the solar system, and they are not fast in the way that a highway speed is fast, or even in the way that a Category 5 hurricane is fast. They are fast in a way that breaks your brain a little when you try to comprehend it. We're talking about sustained wind speeds of over 2,100 kilometers per hour. That is roughly 1,200 miles per hour. That is faster than the speed of sound on Earth. Let that sink in for a moment as you lie there in your warm, windless room. On Neptune, the air itself moves faster than a bullet from certain firearms, and it does this not in brief gusts or localized jets, but across vast swathes of the planet, consistently, relentlessly, as though someone left a cosmic fan on the highest setting and lost the remote. To put this in some earthly perspective, the strongest winds ever recorded on our planet occurred during Tropical Cyclone Olivia near Barrow Island, Australia, in 1996, clocking in at about 407 kilometers per hour. That was enough to rip roofs off buildings, flatten trees, and generally rearrange the landscape in ways that nobody appreciated. Neptune's winds are roughly 5 times faster than that. If you could somehow transplant a Neptune-strength wind to Earth's surface, It would not just destroy buildings, it would scour the ground clean. It would strip soil from bedrock. It would turn pebbles into high-velocity projectiles and sand into something resembling a plasma cutter. The phrase fresh breeze does not apply here. This is wind as a geological force, wind as a weapon, wind as something almost incomprehensible happening on a world that by all reasonable expectations should be calm. And that is the part that keeps scientists awake at night, sometimes quite literally. Neptune should not have these winds. It has no business having them. The planet receives about 900 times less solar energy than Earth does. Sunlight at Neptune's distance is so feeble that noon on Neptune looks roughly like deep twilight on Earth. That strange purple-grey light you get about 40 minutes after sunset, when you can still see shapes, but all the colour has drained away. Solar energy is what drives weather on the inner planets. The sun heats the atmosphere unevenly, warm air rises, cool air sinks, pressure gradients form, and wind is the result. More solar energy generally means more atmospheric activity. This is why Venus, closer to the Sun, has powerful atmospheric circulation, and why Mars, farther away, has relatively gentle breezes most of the time. By this logic, Neptune should be an atmospheric graveyard, a frozen ball of gas with barely enough energy to stir a cloud. Instead, it has the most violent winds in the solar system. Something else is driving them, and figuring out what that something is has been one of the great puzzles of planetary science for over 3 decades. One leading hypothesis points to Neptune's internal heat, which we will explore more deeply soon. The planet radiates about 2.6 times more energy than it receives from the Sun, meaning there is a powerful heat source deep inside that is pumping energy into the atmosphere from below. This internal heat could create steep temperature gradients between the deep interior and the frigid cloud tops, and those gradients could drive ferocious convective cycles that translate into extreme wind speeds. In other words, Neptune's winds might not be powered by the Sun at all. They might be powered by the planet itself, like a self-contained weather engine running on its own internal furnace. Researchers still argue whether this internal heating alone is sufficient to explain the observed wind speeds, or whether other factors, such as the low atmospheric friction on a planet with no solid surface, play a critical role. The low friction idea is interesting because it suggests that once winds get going on Neptune, there is very little to slow them down. No mountains, no continents, no coastlines. Just smooth, deep, endless atmosphere where momentum can build and build without interruption. Here is a delightfully strange detail that tends to surprise people. Neptune's fastest winds actually blow in the opposite direction to the planet's rotation. The equatorial winds streak westward, retrograde, at those record-breaking speeds, while winds at higher latitudes blow eastward, prograde, in the same direction as the rotation. This pattern of alternating wind bands is similar to what we see on Jupiter and Saturn, but the sheer magnitude of Neptune's retrograde equatorial jet is unmatched. Nobody expected a planet this cold and this far from the Sun to have an equatorial jet stream that could outrun sound. It is the planetary equivalent of finding a race car engine inside a golf cart. The exterior says quiet retirement, but under the hood something extraordinary is happening. You think about that wind for a moment, not with fear, but with a kind of drowsy wonder. Somewhere out there, right now, as you lie perfectly still and the air around you barely moves, Neptune's atmosphere is howling at supersonic speeds in total darkness, driven by forces we still do not fully understand. It has been doing this for billions of years. It will keep doing it long after every telescope on Earth has crumbled to dust. There is something humbling about a wind that old, that fast, that indifferent to whether anyone ever measures it. Now you sink a little deeper, past the cloud tops, past the howling winds, past the methane haze and into the crushing interior of Neptune, where something truly absurd is happening. It is raining diamonds, not metaphorical diamonds, not poetic diamonds, actual literal diamonds, formed from carbon atoms being squeezed together under pressures so extreme that they have no choice but to crystallize into the hardest natural substance known to science. This is one of those facts about the solar system that sounds like it was invented by a screenwriter who had run out of plausible ideas, but it is supported by serious physics, laboratory experiments, and decades of theoretical modelling. Inside Neptune, diamonds fall like hailstones through a thick, hot, alien ocean, sinking toward the core in a glittering cascade that no human eye will ever witness. And you thought your weather was dramatic? The basic mechanism is surprisingly straightforward once you get past the sheer absurdity of it. Neptune's atmosphere is composed primarily of hydrogen and helium, but it also contains a significant amount of methane, about 2% by volume. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms, and in the relatively mild conditions of Neptune's upper atmosphere, it behaves like a normal gas. But as you descend deeper into the planet, the pressure and temperature increase relentlessly. A few thousand kilometers below the visible cloud tops, conditions become extreme enough to crack methane molecules apart, stripping the carbon atoms free from their hydrogen partners. Under the immense pressure, which can exceed hundreds of thousands of times the atmospheric pressure on Earth's surface, those liberated carbon atoms are forced into a diamond crystal lattice. They solidify, they become gemstones. And because diamond is denser than the surrounding fluid, these newly formed crystals begin to sink, falling deeper and deeper into Neptune's interior like stones dropped into a thick, hot soup. This idea was first proposed theoretically in the 1980s, around the same time Voyager 2 was making its approach. Planetary scientist Marvin Ross published a landmark paper in 1981 suggesting that the high-pressure, high-temperature conditions inside Uranus and Neptune would be sufficient to convert carbon from methane into diamond. At the time, it was a bold prediction, the kind of hypothesis that earned you either admiration or raised eyebrows depending on the audience. But over the following decades, experimental evidence began to pile up in its favour. In 2017, a team at the SLAC National Accelerator Laboratory used an incredibly powerful optical laser to recreate the conditions found deep inside Neptune by blasting polystyrene, a material with a similar carbon-to-hydrogen ratio as methane, with intense shock waves. And it worked. Under those extreme pressures and temperatures, the carbon atoms in the polystyrene crystallized into nanoscale diamonds. The researchers had essentially made it rain diamonds in a laboratory, which is either the most impressive or the most excessive science experiment ever conducted, depending on your perspective. More recent experiments have refined our understanding further. A 2022 study pushed the boundaries even more by using polyethylene terephthalate, a common plastic, as the starting material, and found that the addition of oxygen, which is also present in Neptune's interior, actually promoted diamond formation. The diamonds formed more easily and grew larger in the presence of oxygen, suggesting that the diamond rain inside Neptune might be even more prolific than earlier models predicted. Researchers still argue about the exact depth at which diamond formation begins, the size of the crystals, and how far they sink before encountering conditions that might melt or dissolve them. But the fundamental concept of diamond precipitation inside ice giants is now widely accepted in the planetary science community. Here is a quirky thought experiment that some scientists have entertained. If diamonds are continuously forming and sinking inside Neptune, where do they end up? One possibility is that over billions of years, a thick layer of diamond has accumulated around Neptune's core, forming a shell of crystallized carbon surrounding whatever rocky or metallic material sits at the very center of the planet. Neptune might, in other words, have a diamond mantle, an entire geological layer made of gemstone. The total mass of diamond inside Neptune could be staggering, potentially millions of times the total amount of diamond that has ever been mined on Earth throughout all of human history. Not that it does anyone any good. Those diamonds are locked away under pressures that would crush any conceivable mining equipment into atoms at temperatures hot enough to melt steel, buried inside a planet that took Voyager 12 years to reach. The universe has a truly exquisite sense of humour when it comes to putting valuable things in inaccessible places. There's also the question of what all this diamond rain means for Neptune's energy budget, and this connects back to the mystery of the planet's internal heat that we brushed against when talking about those impossible winds. As diamonds form and sink through the interior, they convert gravitational potential energy into heat through friction with the surrounding fluid. This process, called gravitational differentiation, could be a significant source of internal heating, essentially turning Neptune into a planet that is partly warmed by the slow, continuous settling of precious gemstones through its guts. It is one of the most elegant and bizarre energy sources imaginable, and it might help explain why Neptune radiates so much more heat than it receives from the Sun. You lie there turning that idea over in your mind. A planet warmed by falling diamonds. It sounds like something from a dream, which is convenient because you're getting closer to one. That warmth you just imagined, the gentle heat of diamonds settling through Neptune's interior, is part of a much larger and much stranger puzzle. Neptune radiates approximately 2.61 times more energy into space than it absorbs from the Sun. This is not a subtle imbalance. It is not a rounding error. The planet is actively and significantly glowing with heat that does not come from sunlight, and understanding where that energy comes from has been one of the most persistent mysteries in planetary science since Voyager 2 first measured it in 1989. You would think that a planet sitting in the deep freeze of the outer solar system, bathed in twilight so dim it barely qualifies as illumination, would be cold all the way through. And on the surface, it is. Neptune's cloud tops hover around minus 218 degrees Celsius, making it one of the coldest places in the solar system. But beneath that frozen exterior, something is cooking. The comparison with Uranus makes this mystery even more puzzling. Uranus and Neptune are often described as twin planets. They are similar in size, similar in mass, similar in composition, and sit in the same general neighbourhood of the outer solar system. You would expect them to behave similarly in terms of energy balance. But Uranus radiates almost no excess heat at all. Its energy output is barely distinguishable from what it receives from the Sun. It is thermally quiet, almost suspiciously so, like a house where the heating has been turned off for so long that the walls themselves have forgotten what warmth feels like. Neptune, by contrast, is practically feverish. Two planets that look like siblings on paper have wildly different internal temperatures, and nobody has a fully satisfying explanation for why. Several hypotheses have been proposed over the years, and they range from the plausible to the delightfully speculative. The most commonly cited mechanism is the one we just encountered in the previous section: gravitational differentiation. As heavier materials like diamond crystals or dense fluids sink toward Neptune's core and lighter materials rise, the resulting friction and compression generate heat. This is essentially the same process that heated the early Earth during its formation, when heavy iron sank to the centre and lighter silicates floated upward, releasing enormous amounts of thermal energy in the process. On Neptune, this differentiation might still be happening today, billions of years after the planet formed, providing a slow but steady trickle of heat from the inside out. The diamond rain we talked about would be a major contributor to this process, turning the continuous formation and settling of carbon crystals into a long-term planetary heating system, but gravitational differentiation alone may not be enough to account for all of Neptune's excess heat. Some researchers have suggested that residual heat from the planet's formation could still be leaking out. When Neptune formed roughly 4.5 billion years ago, the process of accretion gathering up gas, ice and rock from the surrounding solar nebula generated tremendous thermal energy. A planet as massive as Neptune takes a very long time to cool down, and it is possible that it's still slowly releasing the heat of its own birth. Think of it like a massive pot of soup taken off the stove. Even after billions of years, the centre might still be warm. This explanation is elegant in its simplicity, but it runs into problems when you try to apply it to Uranus. If both planets formed in similar ways and at similar times, why has Uranus cooled down so efficiently while Neptune has not? Researchers still argue whether the answer lies in differences in internal structure, composition, or some catastrophic event early in Uranus's history, perhaps a giant impact that disrupted its internal heat distribution. A more exotic suggestion involves the behaviour of hydrogen and helium at extreme pressures. Deep inside Neptune, hydrogen may exist in a metallic state, a phase of matter where hydrogen atoms are squeezed so close together that their electrons become free-flowing, turning the element into something resembling a liquid metal. The separation of hydrogen and helium in this metallic layer, with helium droplets raining out of the hydrogen like oil separating from water, could generate additional heat through a mechanism similar to diamond rain but involving different materials. This helium rain hypothesis has been more commonly discussed in the context of Jupiter and Saturn, but some models suggest it could play a role inside Neptune as well, adding another layer of complexity to an already complicated picture. Here is a fringe idea that surfaces occasionally in the literature and deserves a mention just for its sheer audacity. A small number of theorists have speculated that exotic chemical reactions deep in Neptune's interior, involving compounds behaving in ways we cannot replicate in any laboratory on Earth, might contribute to heat generation. Supersonic water, a bizarre phase of matter where oxygen atoms lock into a crystal lattice while hydrogen ions flow freely through it like a liquid, has been demonstrated to exist at Neptune-like pressures and temperatures. The formation and behaviour of supersonic water could release energy in ways that are not yet fully understood, potentially contributing to the planet's mysterious heat surplus. It is the kind of idea that sits right on the boundary between cutting-edge science and educated guessing, which is exactly where the most interesting science tends to live. You let all of that settle into the background of your thoughts. Somewhere out there, a planet is warming itself with falling diamonds, ancient birth heat, and possibly substances that behave in ways our physics can only approximate. Neptune runs on its own engine, independent of the Sun, burning fuel that no one can fully identify, and it has been doing so for longer than life has existed on Earth. Now you drift sideways, away from the heat and the pressure, and towards something equally baffling but in a completely different way. Neptune's magnetic field is broken. Not broken in the sense that it does not work, because it very much does, but broken in the sense that it looks like it was assembled by someone who had never seen a magnetic field before, and was working from a badly translated instruction manual. Every other planet with a significant magnetic field, Earth, Jupiter, Saturn, has a field that is more or less aligned with its rotational axis and centered roughly on the middle of the planet. This makes intuitive sense. The magnetic field is generated by churning conductive fluid deep in the interior, and since the planet spins on a particular axis, the field tends to line up with that spin, like a bar magnet shoved through the center of a spinning ball. Neat, tidy, predictable. Neptune looked at that convention and apparently decided it was optional. Neptune's magnetic field is tilted approximately 47 degrees away from its rotational axis, 47 degrees. To visualize this, imagine Earth's magnetic North Pole sitting somewhere around the latitude of Miami instead of up near the Arctic. That alone would be strange enough, but Neptune goes further. The field is not even centered on the planet. It is offset from Neptune's geometric center by about 13,500 kilometers, roughly 55% of the planet's radius. This means the magnetic field is dramatically stronger on one side of the planet than the other, creating a lopsided, wobbly magnetosphere that tumbles through space like a badly thrown football. The resulting magnetic environment around Neptune is extraordinarily complex, with field lines twisting and reconnecting in patterns that would give a physics textbook a headache. When Voyager 2 first measured this magnetic field during its 1989 flyby, the data initially looked like instrument error. Scientists at the Jet Propulsion Laboratory reportedly checked and rechecked the readings, convinced that something had gone wrong with the magnetometer. But the readings were correct. Neptune's magnetic field genuinely was that tilted and that offset, and it threw a serious wrench into existing theories about how planetary magnetic fields are generated. Here is where it gets particularly interesting for anyone who enjoys a good scientific mystery. Before Voyager 2 reached Neptune, it had already visited Uranus 3 years earlier, and found that Uranus also had a wildly tilted magnetic field, offset from center by a comparable degree. The initial explanation for Uranus's weird field was that Voyager 2 had caught the planet in the middle of a magnetic field reversal, a process that happens on Earth every few 100,000 years when the north and south magnetic poles swap places. During a reversal, Earth's field becomes chaotic and multipolar, and it was suggested that Uranus might simply be experiencing one of these rare transitional states. But then Neptune turned out to have an almost identically strange field. The odds of catching two planets in the middle of simultaneous magnetic reversals were astronomically low. Something else had to be going on. Researchers still argue about what generates Neptune's peculiar magnetic field, but the leading theory involves the structure of the planet's interior. On Earth, the magnetic field is produced by convection currents in the liquid iron outer core, a process called the geodynamo. On Jupiter and Saturn, the dynamo operates in a deep layer of metallic hydrogen. But Neptune does not have a metallic hydrogen layer thick enough to drive a traditional dynamo, and it almost certainly does not have a liquid iron core like Earth's. Instead, the current thinking is that Neptune's magnetic field is generated in a relatively thin shell of electrically conductive fluid, possibly water, ammonia and methane compressed into an ionic or superionic state, located not at the core but in the planet's mid-layers. This shell dynamo model naturally produces fields that are tilted, offset and multipolar, because the generating region is not deep and central but shallow and asymmetric. The supersonic water we mentioned earlier, that exotic phase where oxygen atoms form a crystalline lattice, while hydrogen ions flow freely, could be a key player here. If a substantial layer of supersonic water exists inside Neptune, the flowing hydrogen ions would constitute an electrical current, and convective motions in this layer could generate a magnetic field. But because this layer sits off-center and does not extend symmetrically through the planet, the resulting field comes out tilted and displaced. It is a beautifully weird solution to a beautifully weird problem. The planet generates its magnetism not from its heart, but from its midsection, like a person whose pulse is strongest in their elbow rather than their chest. A quirky consequence of Neptune's off-center magnetic field is that the magnetosphere, the bubble of magnetic influence that surrounds the planet and deflects the solar wind, is dramatically different in shape and behaviour compared to Earth's. Our magnetosphere is relatively stable and symmetric, a protective cocoon that keeps charged particles from stripping away our atmosphere. Neptune's magnetosphere is a tumbling asymmetric mess that changes configuration as the planet rotates, alternately opening and closing to the solar wind every 16 hours or so. Charged particles get channeled into Neptune's atmosphere along chaotic, shifting pathways, potentially creating auroras that flicker and dance in patterns unlike anything seen on any other planet. No telescope has yet captured these auroras in detail, and whether they are vivid or faint remains a topic of debate, but the physics suggests they would be spectacular in their strangeness. You picture that lopsided magnetic field wobbling through space, a cosmic top spinning slightly off kilter, and there is something almost endearing about it. Neptune does not do anything the conventional way. Not its storms, not its heat, not its magnetic field. It simply exists on its own terms, crooked and magnificent, and now, gently, as though the planet itself is tilting you in a new direction, your attention drifts away from Neptune's blue bulk and toward the most fascinating object in its entire gravitational neighbourhood: Triton, Neptune's largest moon. A world so strange, so out of place, and so full of surprises that some planetary scientists consider it one of the most compelling bodies in the entire solar system. Triton is not just a moon, it is a crime scene. The evidence strongly suggests that Neptune stole it, snatching it from the Kuiper belt billions of years ago in an act of gravitational kidnapping that rearranged the entire Neptunian system and set in motion a chain of consequences that are still playing out today. The first thing that tells you something is deeply wrong about Triton is its orbit. It goes backward. Every other large moon in the solar system, every single one, orbits its parent planet in the same direction the planet rotates. This is called a prograde orbit, and it is what you expect when a moon forms from the same disk of gas and dust that formed the planet, the way our own moon likely coalesced from debris after a giant impact with early Earth. Triton orbits Neptune in the retrograde direction, moving opposite to the planet's spin, like a car driving the wrong way around a roundabout. This is an enormous red flag in planetary science. A large moon in a retrograde orbit almost certainly did not form alongside its planet. It came from somewhere else and was captured. The capture hypothesis is now the dominant explanation for Triton's origin, and the details are both violent and elegant. Triton is believed to have once been a Kuiper belt object, a large icy body orbiting the Sun independently in the vast frozen region beyond Neptune. At some point, probably early in the solar system's history, when the outer planets were still migrating and the Kuiper belt was far more densely populated than it is today, Triton wandered too close to Neptune and was snared by its gravity. But capturing a body as massive as Triton, which is about 2,700 kilometers in diameter, larger than Pluto, is not a simple process. You cannot just grab something that big with gravity alone and park it in a neat circular orbit. The capture would have initially placed Triton in a highly eccentric, elongated orbit, and the process of circularizing that orbit through tidal interactions with Neptune would have released an absolutely staggering amount of energy. This is where the violence comes in. As Triton's orbit gradually circularized, the tidal forces involved would have been enormous, flexing and heating Triton's interior, potentially melting much of its icy body from the inside out. The process would have taken hundreds of millions of years, and during that time, Triton would have been a seething, tidally tortured world, its surface cracking and reshaping under forces that dwarf anything experienced by the moons of the inner solar system. Some models suggest that Triton may have had a global subsurface ocean during this period, liquid water maintained not by sunlight, but by the sheer mechanical energy of tidal deformation. Whether that ocean still exists today, even in diminished form, is one of the most tantalizing unanswered questions in planetary science. But the capture of Triton did not just transform Triton itself, it devastated the pre-existing Neptunian moon system. Before Triton arrived, Neptune almost certainly had a collection of regular, prograde moons that had formed alongside it, similar to the moon systems of Jupiter and Saturn. Triton's arrival on its wild, eccentric, retrograde orbit would have sent gravitational chaos rippling through these original moons, scattering some into space, crashing others into the planet or into each other, and generally wrecking the tidy arrangement that had existed for millions of years. Historians still argue about how many moons Neptune might have lost during this upheaval, but the evidence suggests the destruction was extensive. The small, irregular moons that orbit Neptune today may be fragments and survivors of this catastrophe, remnants of a once orderly system that Triton tore apart on its way in. When Voyager 2 flew past Triton in 1989, it revealed a world that looked like nothing else in the solar system. The surface was extraordinarily young, geologically speaking, with very few impact craters, which meant something had been resurfacing it relatively recently. There were vast plains of frozen nitrogen and methane, strange terrain that scientists nicknamed cantaloupe terrain because it resembled the dimpled skin of a melon, and most astonishingly, active geysers. Voyager 2 observed dark plumes of nitrogen gas and dust shooting up to 8 kilometers above Triton's surface before being caught by thin winds in the moon's tenuous atmosphere and swept downwind into long dark streaks across the ice. Geysers on a moon this cold, this far from the sun, where surface temperatures plunge to minus 235 degrees Celsius, making it one of the coldest measured surfaces in the solar system. The energy driving these eruptions is thought to come from solar heating of subsurface nitrogen ice through a transparent layer of surface ice, creating a greenhouse-like effect that vaporizes material below and eventually blows it through weak spots in the crust. It is a delicate, beautiful mechanism operating at the very edge of thermodynamic possibility. You picture Triton hanging in the dark near Neptune, its surface glistening with frozen nitrogen, dark plumes rising silently into an almost non-existent atmosphere, and you feel the kind of quiet awe that only the strangest places in the solar system can provoke. Triton is not just strange, it is doomed, and the manner of its eventual destruction is so spectacular, so cosmically dramatic, that it deserves its own quiet moment of contemplation as you lie there letting your thoughts unspool. Remember that retrograde orbit, the one that told scientists Triton was a captured interloper rather than a homegrown moon. That same backward orbit is slowly, inexorably killing it. Tidal interactions between Triton and Neptune are gradually draining energy from the moon's orbit, causing it to spiral inward, closer and closer to the planet with each passing eon. The process is fantastically slow by human standards. Triton is currently about 354,800 kilometers from Neptune, and it is losing orbital altitude at a rate that would be imperceptible over 1 million human lifetimes. But the solar system is patient. It has billions of years to work with, and eventually, in roughly 3.6 billion years, give or take a few hundred million, Triton will cross what is known as the Roche limit. The Roche limit is the distance from a planet within which a moon can no longer hold itself together against tidal forces. Beyond this boundary, a moon's own gravity is strong enough to keep it in one piece. Inside it, the difference in gravitational pull between the side of the moon facing the planet and the side facing away becomes greater than the moon's self-gravity, and the object is literally pulled apart. It is named after Edouard Roche, the French astronomer who worked out the mathematics in 1848, just 2 years after Neptune itself was discovered, which is a lovely historical coincidence. Roche could not have known that his theoretical limit would one day be applied to a moon that had not yet been discovered orbiting a planet that had only just been found. When Triton crosses Neptune's Roche limit, the result will be catastrophic and magnificent. The moon will not simply crack into a few large pieces and drift apart. It will be shredded. Tidal forces will fragment Triton into billions of chunks of ice, rock, and frozen nitrogen, spreading the debris into a vast ring around Neptune, and this ring will not be some thin, wispy affair like the faint rings Neptune currently possesses. The mass of Triton is enormous, far greater than the combined mass of Saturn's entire ring system. Neptune's new rings, born from the corpse of its stolen moon, could be the most spectacular ring system in the solar system, dwarfing Saturn's famous bands in mass and possibly in visual grandeur. Saturn, the planet we currently associate with rings more than any other, might eventually have to cede that crown to its distant blue neighbour. Researchers still argue about the precise timeline and the exact characteristics of the resulting ring system. Some models suggest that the destruction of Triton would not be a single event, but a drawn-out process spanning millions of years, with the moon gradually fragmenting as it spirals inward, shedding material in stages rather than all at once. Others propose that once Triton reaches a critical distance, the breakup would be relatively rapid, a geologically sudden event that transforms the Neptunian system in what amounts to the blink of a cosmic eye. The truth probably lies somewhere between these extremes, but either way, the end result is the same. Triton will become a ring. The thief becomes the treasure. Here is a quirky thought that some astronomers have entertained. If intelligent life still exists somewhere in the solar system 3.6 billion years from now, whether on Earth, Mars, or some place we have not yet imagined, they would witness something no human has ever seen: the birth of a major planetary ring system in real time. Every ring system we currently observe, Saturn's, Jupiter's, Uranus's, Neptune's existing faint rings, is already fully formed, and we can only infer how they were created by working backward from their current state. Triton's destruction would offer a front-row seat to ring formation, the ultimate natural experiment in planetary dynamics. Of course, 3.6 billion years is a long time to wait for a show, but the universe has never been in a hurry. The poignancy of Triton's situation is hard to ignore once you know the full story. Here is a world that was once free, an independent body orbiting the sun on its own terms in the Kuiper belt, minding its own frozen business. Then Neptune reached out and grabbed it, hauling it into a retrograde orbit that disrupted everything around it. For billions of years, Triton has orbited its captor, its surface reshaped by tidal forces, its interior heated and cooled and heated again, its original identity as a Kuiper belt object slowly erased. And now, as a final consequence of that ancient capture, it is being dragged inward to its own disintegration. The orbit that trapped it is the orbit that will destroy it. There is a tragic symmetry to that which feels almost literary, as though the solar system is telling a story with a beginning, middle and end, and Triton is the central character who never asked for any of it. You let that narrative settle into you like a slow exhale, a stolen moon spiralling inward through deep time, destined to become something beautiful in its destruction. There is no urgency to the story. It is happening right now, this very moment, Triton drifting imperceptibly closer, the clock ticking on a scale so vast that it makes human concerns feel wonderfully, soothingly small. You have time. Triton has time. Everything has time. And that thought, strangely, is one of the most relaxing things in the universe. From Triton's doomed spiral, your gaze drifts outward now, to the thin, dark structures encircling Neptune itself. The rings. You probably think of Saturn when someone mentions planetary rings, and that is fair because Saturn's rings are the glamorous supermodel of the solar system. bright and sprawling and impossible to miss. Neptune's rings are nothing like that. They are faint, narrow, and composed of some of the darkest material in the solar system, particles so dim that they reflect almost no sunlight, which is why they were not confirmed to exist until Voyager 2 arrived in 1989. If Saturn's rings are a chandelier, Neptune's rings are a cobweb in a basement. You have to know where to look, and even then, you might miss them. But what they lack in spectacle, they make up for in sheer weirdness, because Neptune's rings contain features that should not exist according to the basic rules of orbital mechanics, and explaining them has kept dynamicists busy for decades. Neptune has 5 main rings, named after scientists who contributed to the study of the planet. From innermost to outermost, they are Gala, Leverrier, Lassell, Arago, and Adams. The names are a nice historical touch, a quiet tribute to the humans who helped pull Neptune out of obscurity, and you can almost imagine each ring as a kind of memorial wreath hanging in the dark. Most of these rings are relatively unremarkable, thin bands of dust and ice particles spread evenly along their orbits, behaving the way ring material is supposed to behave. But the outermost ring, the Adams ring, is where things get strange. Within the Adams ring, there are distinct concentrations of material, bright clumps that are significantly denser than the rest of the ring. These clumps are called arcs, and when they were first observed from Earth through stellar occultation experiments in the 1980s, before Voyager 2 even arrived, they caused a minor crisis in planetary ring theory. The crisis was this: ring arcs should not exist. In a normal ring, particles orbit the planet at slightly different speeds depending on their distance from it, with inner particles moving faster and outer particles moving slower. This differential rotation should smear out any clumps within a few years, spreading the material evenly around the entire ring like butter on toast. A stable, long-lived concentration of ring material in one spot is, according to the basic physics, about as likely as a pile of sand on a spinning turntable staying in a neat mound instead of spreading out. And yet, there they were. Voyager 2 confirmed 4 distinct arcs within the Adams ring, which were given wonderfully French names: Liberté, Égalité, Fraternité, and Courage, a naming scheme that makes them sound less like orbital debris and more like a revolutionary manifesto hanging in space. The solution to the arc puzzle, or at least the partial solution, involves a tiny moon named Galatea, which orbits just inside the Adams ring. Galatea is only about 160 kilometers across, a pebble by solar system standards, but its gravitational influence is precisely tuned to interact with the ring particles through a mechanism called a corrotation resonance. In simple terms, Galatea's gravity creates a pattern of gravitational nudges that trap ring material in specific locations along the Adams ring, preventing the natural smearing process from dispersing the arcs. It is a delicate gravitational dance, a tiny moon shepherding particles into formation like a border collie keeping sheep in a huddle. The physics is elegant, the kind of solution that makes you appreciate how gravity can organize matter in unexpectedly subtle ways. But here is the problem. The Galatea resonance model works beautifully on paper, yet observations over the past few decades have shown that the arcs are not as stable as the model predicts. Hubble Space Telescope observations and ground-based adaptive optics studies have revealed that the arcs are changing. The Liberté arc has faded significantly since Voyager 2 observed it, while other arcs have shifted in positional brightness. Researchers still argue about whether this means the resonance model is incomplete, whether additional moons or mechanisms are involved, or whether the arcs are simply transient features that will eventually dissipate and reform on timescales of decades or centuries. The rings of Neptune, it seems, are not a fixed structure, but a living system, constantly evolving under the competing influences of gravity, collisions, and the slow erosion of particles by micrometeorite impacts and radiation. A quirky historical footnote about Neptune's rings involves none other than the astronomer William Lassell, who discovered Triton just 17 days after Neptune itself was found in 1846. Lassell also claimed to have observed a ring around Neptune, but other astronomers could not confirm his sighting, and the claim was eventually dismissed as an optical artifact caused by his telescope. For over a century, Lassell's ring was considered a mistake. Then Voyager 2 arrived and confirmed that Neptune did indeed have rings, exactly where Lassell might have glimpsed something. Historians still argue whether Lassell actually saw the rings or whether the coincidence is just that, a coincidence. But there is something satisfying about the possibility that a 19th century astronomer with a homemade telescope in Liverpool caught a faint shimmer of something that would take 143 years and a robotic spacecraft to confirm. You think about those dark, clumpy rings hanging in the black around Neptune, held together by the gentle gravitational persuasion of a moon too small to see without a spacecraft, and the image has a fragile beauty to it. Everything about Neptune's rings feels temporary, provisional, like a sketch that might be erased and redrawn at any moment. Nothing lasts forever out there, not the storms, not the arcs, and eventually not even the rings themselves. Beyond the rings and beyond Triton, Neptune's gravitational reach extends into a chaotic swarm of small, misfit moons that orbit in every conceivable direction, at every conceivable angle, like a cloud of confused bees around a very large and very blue hive. As of the most recent count, Neptune has 16 confirmed moons, though that number has been creeping upward as telescopes and survey techniques improve, and it would not be surprising if more are lurking out there waiting to be found. Triton dominates the system so completely, containing more than 99.5% of the total mass orbiting Neptune, that everything else is essentially an afterthought. But those afterthoughts have stories of their own, and the stories are wild. The moons of Neptune fall into two broad categories. The inner regular moons orbit close to the planet in neat circular prograde paths, hugging the equatorial plane like well-behaved children. These include tiny bodies like Naiad, Thalassa, Despina and Galatea, the little shepherd moon we just met guarding the Adam's ring arcs. They are small, dark and irregularly shaped, the largest of them barely 200 kilometers across, and they are thought to be relatively young in solar system terms. Not young as in recently formed from scratch, but young as in reassembled. Remember the catastrophic arrival of Triton we talked about earlier, the gravitational wrecking ball that tore apart Neptune's original moon system. These inner moons are likely the descendants of that destruction, fragments and rubble that gradually reaccreted into new bodies after the chaos subsided. They are in a sense the children of a disaster, built from the wreckage of their predecessors. Then there are the outer irregular moons, and these are a completely different breed. They orbit far from Neptune, in highly elliptical and often steeply inclined orbits, and most of them are retrograde, orbiting in the opposite direction to Neptune's rotation. Their orbits are so elongated and tilted that they barely seem connected to Neptune at all, like distant relatives who show up to family gatherings, but sit in the corner and refuse to make eye contact. The most notable of these is Nereid, discovered in 1949 by Gerard Kuiper, the same astronomer whose name would later be attached to the Kuiper belt. Nereid has one of the most eccentric orbits of any moon in the solar system, swinging from about 1.4 million kilometers from Neptune at its closest approach to over 9.6 million kilometers at its farthest, a seven-fold variation that takes roughly 360 Earth days to complete. Its orbit is so stretched out that it spends most of its time far from Neptune, looping through space on a path that looks more like a comet's trajectory than a moon's. Nereid's bizarre orbit is almost certainly another consequence of Triton's capture. Before Triton arrived, Nereid may have had a much more normal circular orbit. The gravitational perturbation caused by Triton's entry into the system would have yanked Nereid out of its original path and flung it into the eccentric orbit it occupies today. Nereid is, in this interpretation, a survivor of the Triton catastrophe, a moon that was not destroyed or ejected but was permanently scarred, its orbit twisted into something unrecognizable. Researchers still argue about whether Nereid is a native Neptunian moon that was perturbed or a captured Kuiper belt object that arrived independently. But the perturbation hypothesis remains the most widely accepted. More recently, the family of Neptunian moons has been growing through dedicated survey campaigns using large ground-based telescopes. In 2013, a tiny moon designated S/2004N1, later named Hippocamp, was discovered hiding in Hubble Space Telescope images. Hippocamp is absurdly small, only about 34 kilometers in diameter, making it the smallest known moon of Neptune and one of the smallest moons in the entire solar system to be individually detected and named. It orbits remarkably close to the much larger moon Proteus, which is about 420 kilometers across, and some researchers have suggested that Hippocamp may actually be a fragment of Proteus, knocked loose by a large impact at some point in the past. If true, this means Hippocamp is not just a moon, but a piece of a moon, a chip off the old block in the most literal sense, orbiting alongside its parent like a splinter that never quite drifted away. Here is a quirky detail that illustrates just how much we still do not know about Neptune's moons. In 2021, astronomers announced the discovery of several new irregular moon candidates around Neptune using deep survey data, and some of these objects are so small and so faint that confirming their orbits requires years of follow-up observations. The outer solar system is littered with tiny bodies, and determining whether a given speck of light is a moon of Neptune or a passing Kuiper belt object just happens to be in the neighbourhood at the time of observation is surprisingly difficult. The boundary between moon and not moon gets blurry when you're dealing with objects only a few kilometers across in orbits that take decades to complete. It is the cosmic equivalent of trying to figure out whether a particular cat belongs to your neighbour or is just a stray that keeps showing up in the yard. The collective portrait of Neptune's moon system is one of violence, capture and reconstruction. Unlike the orderly satellite families of Jupiter and Saturn, which largely formed in place and have orbited in predictable patterns for billions of years, Neptune's moons bear the scars of a system that was shattered and rebuilt. Triton dominates everything, a stolen giant whose arrival changed the rules for every other body in Neptune's gravitational domain. You picture all those tiny moons tumbling through the dark, each one a fragment of a story that began billions of years ago with one rogue world wandering too close to a blue giant, and the image is both violent and strangely peaceful from this distance. You're drifting now comfortably through the history of Neptune's moons and rings, and it's time to pull back even further, to zoom out from the planet itself and consider something far grander. Neptune may not have always lived where it lives today. In fact, there is strong evidence that the eighth planet spent its youth much closer to the Sun, in a completely different part of the solar system, before being flung outward to its current address in a gravitational upheaval so dramatic that it reshaped the architecture of the entire solar neighbourhood. This idea is known as planetary migration, and the specific model that describes it most compellingly is called the Nice model, named not because it is pleasant, although it is rather elegant, but because it was developed by scientists working in Nice, France, which is a far more glamorous origin story than most astrophysical theories can claim. The Nice model, first proposed in 2005 by a team including Rodney Gomes, Hal Levison, Alessandro Morbidelli, and Cleonis Tsiganis, begins with a solar system that looks very different from the one you know. In the model's initial configuration, the four giant planets, Jupiter, Saturn, Uranus, and Neptune, all formed much closer together and much closer to the Sun than they are now, occupying a compact arrangement between roughly 5 and 17 astronomical units from the Sun. Beyond them, stretching outward like a vast frozen reservoir, was a massive disk of icy planetesimals, small rocky and icy bodies left over from the solar system's formation. This disk contained perhaps 35 Earth masses of material, a tremendous amount, and it sat quietly beyond the outermost giant planet, waiting to play its role in the coming upheaval. For hundreds of millions of years this arrangement held. The giant planets orbited in relatively stable, nearly circular paths, and the planetesimal disk remained largely undisturbed. But gravitational interactions between the planets and the inner edge of the disk slowly, almost imperceptibly, began to shift things. Jupiter, the most massive planet, gradually migrated inward, toward the Sun, while Saturn, Uranus, and Neptune migrated outward, away from it. This slow drift continued until Jupiter and Saturn crossed a critical gravitational threshold, a mean motion resonance, likely the 2-to-1 resonance, where Saturn's orbital period became exactly twice Jupiter's. When this happened, everything went haywire. The resonance crossing amplified gravitational interactions between the two largest planets, sending shock waves through the orbits of Uranus and Neptune. The ice giants were kicked outward on increasingly eccentric orbits, ploughing directly into the dense planetesimal disk. Neptune, in particular, was hurled into the thick of it, scattering icy bodies in every direction like a bowling ball crashing through a field of pins. Some planetesimals were flung inward, toward the inner solar system, potentially triggering what is known as the Late Heavy Bombardment, a period roughly 3.9 billion years ago when the Moon, Earth, and other inner solar system bodies were pummeled by a sudden surge of impactors. Others were scattered outward into the distant reaches of the solar system, populating the scattered disk and possibly even contributing to the Oort cloud. And Neptune itself, after this violent scattering phase, gradually settled into its current orbit at about 30 astronomical units from the Sun, roughly twice as far out as where it started. Historians still argue about the timing and severity of the Nice model instability. The original version of the model linked it directly to the Late Heavy Bombardment at around 3.9 billion years ago, but more recent work has suggested the instability may have occurred much earlier, perhaps within the first 100 million years after the solar system formed. The revised timeline changes some of the model's implications for the inner solar system, but does not fundamentally alter the story of Neptune's outward migration. Either way, Neptune moved. It travelled billions of kilometres from its birthplace to its current orbit, and in doing so, it sculpted the outer solar system into the shape we observe today. Here is a fringe idea that occasionally surfaces in discussions of planetary migration and deserves a mention for its sheer scope. Some researchers have speculated that the original solar system may have contained a fifth giant planet, an additional ice giant that was ejected entirely from the solar system during the Nice model instability. In simulations, the gravitational chaos of the resonance crossing sometimes results in one planet being flung out on a hyperbolic trajectory, sent hurtling into interstellar space to become a rogue planet drifting between the stars. If this happened, there is a ghost planet somewhere out in the galaxy that was once our neighbour, a sibling of Neptune and Uranus that lost the gravitational lottery and was banished forever. It is the kind of idea that is almost impossible to prove, but equally impossible to definitively rule out, which places it in that delicious territory of science where speculation and rigour shake hands across a very thin line. You let the scale of this story settle over you like a heavy blanket. Neptune is not just a planet sitting in its assigned spot. It is a traveller, a migrant, a world that was born in one place and now lives in another, and the journey between those two places transformed the solar system. The Kuiper belt, the scattered disk, the late heavy bombardment, the very distribution of small bodies throughout the outer solar system, all of it bears Neptune's fingerprints. You close your eyes a little tighter and imagine that migration, slow and immense, a blue giant drifting outward through the dark over millions of years, rearranging everything it passes. And the rearranging did not stop once Neptune settled into its current orbit. The planet did not simply arrive at 30 astronomical units, park itself, and leave everything alone. It kept pushing, kept pulling, kept herding the frozen debris of the outer solar system into patterns and structures that persist to this day. The Kuiper belt, that vast ring of icy bodies stretching beyond Neptune's orbit, exists in its current form largely because Neptune put it there. Without Neptune's gravitational influence, the Kuiper belt would be a very different place, and Pluto, the most famous resident of that icy neighbourhood, would have a very different life. Neptune is not just a planet, it is a shepherd, and the Kuiper belt is its flock. The Kuiper belt extends from roughly 30 astronomical units, just beyond Neptune's orbit, to about 50 astronomical units from the Sun, a broad, flattened donut of frozen objects ranging from tiny chunks of ice a few kilometres across to dwarf planets, hundreds or even thousands of kilometres in diameter. It contains an estimated tens of thousands of objects larger than 100 kilometres and hundreds of millions of smaller bodies, a population so vast that it makes the asteroid belt between Mars and Jupiter look like a minor inconvenience. And the distribution of these objects, the way they are clustered and sorted and arranged, is almost entirely a consequence of Neptune's gravity. The most striking evidence of Neptune's influence is found in the orbital resonances that lock thousands of Kuiper belt objects into precise mathematical relationships with Neptune's orbit. The most famous of these is the 3:2 resonance, occupied by Pluto and a large population of similar objects now collectively called Plutinos. For every 3 orbits Neptune completes around the Sun, Pluto completes exactly 2. This is not a coincidence, it is a gravitational trap. When Neptune migrated outward during the Nice-modelled instability, it swept through the primordial Kuiper belt like a net through water, capturing objects into resonant orbits as it went. Bodies that happened to be in the right place at the right time were gently corralled into these resonances and have remained locked in them ever since, their orbits synchronized with Neptune's in a gravitational waltz that has been playing for billions of years. Pluto is the poster child for this process, but it is far from the only example. There are Plutinos in the 3:2 resonance, Tutinos in the 2:1 resonance, and objects trapped in a whole zoo of other resonances, the 5:3, the 7:4, the 5:2, each one a different mathematical harmony between an object's orbit and Neptune's. The Kuiper belt is not a random scattering of debris, it is a structured, organised system, and Neptune is the conductor. Researchers still argue about whether Neptune's migration was smooth and gradual, which would produce one pattern of resonance populations, or jerky and episodic, which would produce a different pattern, and the distribution of objects in different resonances is one of the key pieces of evidence used to discriminate between migration models. Here is a detail that illustrates Neptune's gravitational dominance in a way that borders on the poetic. Pluto's orbit is highly eccentric, so eccentric that at its closest approach to the Sun, Pluto actually crosses inside Neptune's orbit. For about 20 years out of every 248-year orbital period, Pluto is technically closer to the Sun than Neptune is. You might think this would lead to a collision, or at least a dangerously close encounter, but it never does. The 3:2 resonance ensures that whenever Pluto is at its closest to the Sun, Neptune is on the opposite side of its orbit, safely far away. They are like two dancers on the same stage who never collide because their choreography is perfectly synchronized. Neptune set up this dance billions of years ago when it captured Pluto into resonance, and the two have been performing it flawlessly ever since. It is gravitational engineering on a scale that makes human engineering look like children stacking blocks. A quirky and relatively recent discovery has added another layer to the Neptune Kuiper belt story. In the early 2000s, astronomers began finding a population of Kuiper belt objects that do not fit neatly into any resonance and whose orbits are detached from Neptune's influence entirely. These are the so-called scattered disk objects and extreme trans-Neptunian objects, bodies on wildly eccentric, highly inclined orbits that take them far beyond the classical Kuiper belt. Some of these objects have orbital periods of thousands of years and travel to distances of hundreds of astronomical units from the Sun. How they got onto these extreme orbits is a matter of ongoing debate, and some researchers have controversially suggested that the gravitational influence of an as yet undiscovered large planet, sometimes called Planet 9, might be responsible. Neptune pushed many of these objects outward during its migration, but whether Neptune alone can account for all the orbital structures observed in the distant Kuiper belt, or whether another massive body is lurking out there in the dark, remains one of the most hotly contested questions in modern planetary science. You picture Neptune as a gravitational gardener, tending a vast frozen landscape, pushing objects into rows, trapping them in resonant patterns, scattering the unruly ones to the far edges of the solar system. It is an image that is both powerful and oddly soothing. Everything in the outer solar system has been touched by Neptune, shaped by it, organized by its slow and patient gravity. And the beautiful irony is that Neptune does all of this silently, invisibly, without any visible effort. Just gravity and time and the quiet arithmetic of orbital mechanics working itself out across billions of years. Your breathing matches that rhythm now, slow and steady, as the outer solar system arranges itself around you. Now you sink again, back toward Neptune itself, dropping beneath the screaming winds and the methane haze, past the layers where diamonds crystallize and begin their long descent, deeper still, into a realm so extreme that the very concept of familiar matter starts to lose its meaning. Somewhere inside Neptune, at depths that no instrument has ever directly probed and no spacecraft could ever survive reaching, there may be an ocean. Not an ocean of water in any form you would recognize, not the kind of ocean you wade into on a summer afternoon, with sand between your toes and salt on your lips. This is a superheated, super-pressurized ocean of water, ammonia, and methane, crushed into exotic states of matter that exist nowhere on Earth's surface, and barely exist in our most advanced laboratories. It is an ocean that would kill you instantly in about 15 different ways simultaneously, and yet it may be one of the most important features hidden inside any planet in the solar system. The idea of a deep interior ocean inside Neptune comes from models of the planet's internal structure. Scientists generally divide Neptune's interior into three broad layers. The outermost layer is the atmosphere, composed primarily of hydrogen, helium, and methane, extending down several thousand kilometers. Below that is the mantle, a thick layer of hot, dense fluid made primarily of water, ammonia, and methane, often collectively referred to as ices, even though at the temperatures and pressures found in Neptune's interior, they are nothing like the frozen substances those names conjure. The term ices is a holdover from cosmochemistry, referring to any compound that condenses at temperatures found in the outer solar system, regardless of its actual phase inside a planet. At Neptune's interior conditions, these ices are compressed into superheated fluids at temperatures that may exceed 5,000 degrees Celsius, hot enough to melt steel, yet kept in a liquid or supersonic state by pressures exceeding millions of atmospheres. It is in this mantle layer that the truly exotic physics begins. Remember the supersonic water we touched on earlier, the bizarre phase of matter where oxygen atoms lock into a rigid crystalline lattice while hydrogen ions flow freely through it like a hot electric current. Laboratory experiments conducted in the last decade, using powerful lasers to compress water samples to pressures mimicking Neptune's interior, have confirmed that supersonic water is real and stable at the conditions expected deep inside ice giants. This is a substance that is simultaneously a solid and a liquid, a crystal with a flowing interior, and it may constitute a substantial fraction of Neptune's mantle. The implications are staggering. An entire layer of Neptune, thousands of kilometers thick, may be made of a material that has no analogue anywhere on Earth's surface, a material that was purely theoretical until a few years ago. The ocean buried inside Neptune would not have a surface in the traditional sense. There would be no clear boundary where atmosphere ends and ocean begins, no coastline, no horizon. Instead, there would be a gradual transition, the hydrogen-helium atmosphere becoming denser and hotter with depth, until it seamlessly blends into the water-ammonia-methane fluid of the mantle. It is less like diving into the sea, and more like walking into an increasingly thick fog that slowly becomes a liquid around you, if that fog were also several thousand degrees and pressing on you with the weight of a continent. Researchers still argue about the exact depth at which this transition occurs and whether it is sharp or gradual. But most models place the beginning of the mantle region somewhere between 7,000 and 10,000 kilometers below the visible cloud tops. Here is a quirky detail about the behavior of water under extreme pressure that makes Neptune's interior even stranger. At pressures above about 50 gigapascals, roughly 500,000 times Earth's atmospheric pressure, water can exist in a phase called Ice 18, which is the supersonic state. But at even higher pressures, deeper inside Neptune, water may transition into other exotic phases that have barely been characterized. Some theoretical models predict the existence of phases where both hydrogen and oxygen atoms are locked into crystal structures, creating ultra-dense forms of ice that are harder than most minerals found on Earth's surface. Neptune's deep interior may contain layers of ice that are nothing like the ice in your freezer. Materials so dense and so hard that they would make diamonds seem fragile by comparison. The fact that we casually use the word ice to describe these substances is one of the great misnomers in planetary science, the kind of linguistic shortcut that hides an entire universe of strangeness behind a familiar word. The potential existence of this deep ocean matters for reasons beyond pure curiosity. The electrical conductivity of the supersonic water and ionic fluids in Neptune's mantle is central to the planet's magnetic field, that tilted off-center magnetic puzzle we explored earlier. It is also relevant to Neptune's thermal evolution, because convective motions in the mantle transport heat from the deep interior to the outer layers, driving the atmospheric dynamics that produce those impossible winds. Everything connects inside Neptune. The ocean feeds the magnetic field shapes the magnetosphere, the convective heat from the mantle drives the weather, and the weather produces storms that appear and vanish on the cloud tops. You're looking at a single integrated system, a planet-sized engine where every component depends on every other component, and at the heart of it all is a scalding, crushing, alien ocean that no human will ever touch. You imagine it for just a moment. That impossible ocean, glowing with heat in the absolute dark, existing under pressures that would compress your entire body into something the size of a coin, and instead of feeling frightened, you feel a kind of sleepy awe. It is too far away to hurt you. It is too strange to fully comprehend. It simply exists, hidden inside a blue sphere at the edge of everything, keeping its secrets warm. Speaking of blue, you've probably been wondering about that colour. That vivid, electric, almost impossibly saturated blue that makes Neptune one of the most visually striking objects in the solar system. When Voyager 2 sent back its images in 1989, Neptune looked like a sapphire dropped into the void, a deep azure that seemed too perfect to be natural. And for a long time, the explanation for that colour seemed straightforward: methane. Neptune's atmosphere contains about 2% methane, and methane gas absorbs red wavelengths of light, while allowing blue wavelengths to scatter and reflect back to the observer. Red light goes in, blue light comes out, and you get a blue planet. Simple, clean, case closed. Except it was not closed at all, because there was a nagging problem sitting right next door, and that problem was named Uranus. Uranus also has methane in its atmosphere, roughly the same proportion as Neptune, give or take, and yet Uranus is not the same shade of blue. Uranus appears as a pale, washed-out cyan, a greenish blue that looks almost sickly compared to Neptune's rich azure. If methane absorption were the whole story, the two planets should look virtually identical, because they have virtually identical methane concentrations. The fact that they look noticeably different meant that something else was happening, some additional factor in one or both atmospheres that was modifying the colour beyond what methane alone could produce. For decades, this colour discrepancy was one of those mildly embarrassing gaps in planetary science, the kind of question that kept showing up in textbook margins and student exam papers without a fully satisfying answer. The breakthrough came in 2022, when a team of researchers led by Patrick Irwin at the University of Oxford published a study that proposed a comprehensive model of the atmospheric haze layers on both planets. Using data from the Hubble Space Telescope, the Near-Infrared Spectrograph on Gemini North, and the NASA Infrared Telescope facility, the team constructed a model with 3 distinct aerosol layers in each planet's atmosphere. The deepest layer, sitting well below the visible cloud deck, was found on both planets and behaved similarly. The middle layer was a haze of photochemically produced particles, created when ultraviolet sunlight breaks down methane molecules in the upper atmosphere, and the resulting fragments recombine into complex hydrocarbon compounds that condense into tiny particles. This middle haze layer is where the crucial difference lies. On Uranus, this haze layer is significantly thicker than on Neptune, and the extra haze acts as a whitening agent, scattering light more broadly across all wavelengths, and washing out the deep blue that would otherwise result from methane absorption alone. Neptune, with a thinner haze layer, allows more of the pure methane blue to shine through, giving it that rich, saturated colour. The reason for the difference in haze thickness is thought to be related to atmospheric circulation. Neptune's atmosphere, as we have already established, is far more energetic and dynamic than Uranus's. The vigorous convective mixing on Neptune is more efficient at cycling haze particles through the atmosphere, breaking them up and transporting methane snow to deeper levels where it can precipitate out, effectively cleaning the atmosphere and keeping the haze layer thin. Uranus, with its sluggish, less active atmosphere, allows the haze to accumulate and thicken, creating that characteristic pale, muted appearance. It is, in essence, a story about atmospheric housekeeping. Neptune keeps its windows clean, and Uranus lets the grime build up. Researchers still argue about the precise mechanisms driving the difference in atmospheric mixing rates, particularly since both planets have similar rotation periods. But the haze model has been widely regarded as the most convincing explanation to date. Here is a quirky footnote that complicates the story even further. The Voyager 2 images that made Neptune famous may have exaggerated its blueness. The raw images returned by the spacecraft were processed and enhanced by the imaging team to bring out atmospheric detail, and in the process the contrast and colour saturation were boosted beyond what the human eye would actually perceive. True colour reprocessing of the Voyager 2 data suggests that Neptune, while still distinctly bluer than Uranus, is not quite as dramatically blue as the iconic images imply. The Neptune you see in most textbooks and documentaries is, in a sense, a slightly enhanced version of reality, a portrait with the saturation turned up. This does not diminish Neptune's beauty, but it does add an interesting layer of complexity to how we perceive and represent distant worlds. The most famous image of Neptune is both real and slightly idealized, a kind of planetary glamour shot where the camera angles were just right and the lighting was carefully adjusted. There is also the matter of seasonal colour changes. Because Neptune has an axial tilt of about 28 degrees, similar to Earth's, it experiences seasons as different hemispheres receive more or less sunlight over the course of its 165-year orbit. Hubble observations spanning decades have detected subtle changes in Neptune's brightness and cloud patterns that correlate with its seasonal cycle, suggesting that the haze production and atmospheric circulation patterns shift over time. The Neptune we see today may look subtly different from the Neptune our grandchildren will observe, a planet whose shade of blue gradually ebbs and flows over centuries like the world's slowest mood ring. You let that image play behind your eyelids, a planet slowly blushing and fading over timescales so vast that no single human lifetime could notice the change. It is the gentlest kind of transformation, invisible unless you're patient enough to watch for 100 years. And patience is something Neptune demands in almost every respect, because this planet does nothing quickly. Its orbit around the Sun takes approximately 164.8 Earth years to complete, which means that since its discovery in 1846, Neptune has completed exactly one full orbit, finishing its first observed lap in 2011. Think about that for a moment. Every significant event in modern human history, both world wars, the invention of the automobile, the telephone, the airplane, the computer, the moon landing, the rise and fall of empires, the entire arc of the 20th century, all of that fits inside a single Neptunian year. A creature born on Neptune at the moment of its discovery would have celebrated its first birthday only recently, and it would still be waiting quite a while for its second. Time moves differently when you're that far from the Sun, and on Neptune a single year contains lifetimes. This enormous orbital period, combined with Neptune's axial tilt of about 28.3 degrees, produces seasons that are almost incomprehensibly long by Earth standards. Each Neptunian season lasts roughly 40 Earth years. 40 years of spring, followed by 40 years of summer, 40 years of autumn, and 40 years of winter. The seasonal cycle that we experience in a single year, with its comforting rhythm of warming and cooling, blooming and withering, takes well over a century and a half to unfold on Neptune. You could be born at the start of a Neptunian summer and grow old before autumn arrived. Your children could live their entire lives during autumn. Your grandchildren might see the first snows of winter, if you could call anything on Neptune snow in any meaningful sense. The effects of these ultra-long seasons on Neptune's atmosphere have been one of the most fascinating observational projects in modern planetary science. Though project is perhaps a generous word for something that requires decades of telescope time to yield meaningful results. When Voyager 2 flew past in 1989, Neptune's southern hemisphere was in the middle of its summer, tilted toward the Sun, and the images revealed a dynamic atmosphere full of storms, bright cloud bands, and that famous Great Dark Spot. In the years since, as Neptune has slowly progressed through its orbit, astronomers using Hubble and increasingly powerful ground-based telescopes have watched the planet's appearance change, subtly but measurably, as the seasons advance. One of the most striking observations came in 2003, when astronomers noticed that Neptune's south pole appeared significantly brighter than the rest of the planet. This brightening was attributed to increased upwelling of methane-rich gas in the polar region, which condensed into bright methane ice clouds at high altitudes as the South Pole received maximum solar heating during its extended summer. It was the first direct evidence that Neptune's atmosphere responds to seasonal forcing, that even the tiny amount of sunlight reaching this distant world is enough to drive detectable changes in cloud formation and atmospheric circulation over decades. This was not a given. Some scientists had suspected that Neptune's powerful internal heat source would overwhelm any seasonal effects, driving the atmosphere primarily from below rather than from above. The observation that both internal heat and solar forcing play roles makes Neptune's atmospheric dynamics a complex two-source system, and researchers still argue about the relative importance of each driver. Here is a particularly quirky detail about Neptune's seasons that highlights how much we do not know. Because Neptune's orbital period is so long, and because telescopic technology capable of resolving atmospheric detail on Neptune has only existed for a few decades, we have observed less than a quarter of a single Neptunian year in any meaningful detail. Our understanding of Neptune's seasonal cycle is roughly equivalent to someone who has only experienced spring trying to predict what winter will be like. We know summer in the southern hemisphere produced bright polar clouds and vigorous storm activity. We can see hints that as autumn approaches, the cloud patterns are shifting. But what Neptune looks like during its northern summer, or during the equinoxes when neither pole is strongly illuminated, remains largely a matter of models and educated guesses. The next Neptunian equinox will not occur until approximately 2046, and the northern summer solstice will not arrive until around 2090. Anyone hoping to observe a complete seasonal cycle on Neptune will need to be extraordinarily patient or extraordinarily long-lived, preferably both. There is something deeply meditative about Neptune's relationship with time, and it feels appropriate to sit with it as your body grows heavier against whatever surface is holding you. 40-year seasons, a year that spans the entirety of modern history, storms that bloom and die in the time it takes a Neptunian week to pass, which itself is only about 16 hours, because despite its vast size and slow orbit, Neptune spins remarkably fast. A day on Neptune lasts just 16 hours and 6 minutes, one of the shortest days in the solar system, which means the planet is simultaneously one of the slowest travellers and one of the fastest spinners in our cosmic neighbourhood. It is a world of contradictions, glacially slow in its journey around the sun, furiously fast in its rotation, patient beyond all human comprehension in its seasons, yet violent and ephemeral in its storms. You breathe in on one timescale and out on another, and Neptune keeps spinning, neither hurrying nor waiting, simply turning in the dark at its own ancient pace. And now, still drifting, still settling deeper into the cushion of your own relaxation, you arrive at a question that seems almost absurd to ask, but which a small and growing number of scientists have asked with entirely straight faces. Could anything be alive on Neptune? Not on the surface, because Neptune does not have a surface in any conventional sense. Not on the frozen cloud tops, where temperatures plunge to minus 218 degrees Celsius, and the air is a thin haze of hydrogen and methane. But somewhere in between, in the vast vertical span of Neptune's atmosphere, there may be a zone where conditions are not entirely hostile to biology, or at least not hostile to the kind of biology we have not yet imagined. The idea is borrowed from a concept that has been discussed more seriously in the context of Jupiter and Venus, the notion of atmospheric habitable zones. On Earth, life exists almost everywhere, from boiling hydrothermal vents to frozen Antarctic lakes, from the upper atmosphere to the deep ocean floor. The key ingredients, liquid water, energy, and organic chemistry, are found in a wide range of environments. In the atmospheres of giant planets, there are altitude bands where the temperature and pressure fall within ranges that could, theoretically, support liquid water droplets. On Neptune, at a depth where the atmospheric pressure reaches roughly 1 to 2 bars, similar to Earth's surface pressure, the temperature rises to somewhere between 0 and a few hundred degrees Celsius, depending on the exact depth and the local conditions. In this zone, the physics alone does not rule out the existence of liquid water, and the atmosphere contains methane, ammonia, and hydrogen sulfide, all of which are potential sources of chemical energy for hypothetical organisms. This is, to be very clear, an extraordinarily speculative idea. Nobody is claiming that Neptune is likely to harbour life. The atmospheric habitable zone, such as it is, would be a brutal environment by any standard. The winds are supersonic. The atmosphere is turbulent and convective, meaning any organism would be constantly swept upward into lethally cold regions, or downward into lethally hot ones. There is no solid surface to anchor to, no stable environment in which to build a home. Any life form existing in Neptune's atmosphere would need to be a free-floating organism, something like a microbe drifting in an eternal tempest, extracting energy from chemical reactions in the surrounding gas and somehow reproducing before being shredded, frozen, or cooked by the planet's relentless atmospheric dynamics. It is not impossible in the strictest sense of the word, but it is about as improbable as you can get while still being worth mentioning at a scientific conference, without getting laughed out of the room. Researchers still argue about whether the concept of atmospheric life on gas and ice giants is a legitimate avenue of scientific inquiry or a fringe distraction from more productive areas of astrobiology. The mainstream focus of the search for extraterrestrial life remains firmly on places like Europa, Enceladus, and Mars, worlds with solid surfaces, subsurface oceans, and more hospitable conditions. But a few voices in the community have pointed out that we define habitability based on Earth life, and Earth life is the only life we know. If biology can arise from fundamentally different chemistry, using solvents other than water and metabolic pathways we have not conceived of, then the deep atmospheres of ice giants cannot be categorically ruled out. It is the kind of argument that is philosophically sound but practically untestable, with current technology, which places it in a frustrating limbo between imagination and science. Here is a quirky historical connection that adds some charm to this otherwise speculative discussion. Carl Sagan, the legendary astronomer and communicator, was one of the first scientists to seriously consider the possibility of life in the atmospheres of giant planets. In a 1976 paper co-authored with Edwin Salpeter, Sagan described hypothetical organisms he called floaters, sinkers, and hunters that could theoretically inhabit the atmospheric layers of Jupiter. Floaters would be enormous, balloon-like creatures that maintain their altitude by controlling their buoyancy, feeding on organic molecules carried by atmospheric currents. Sinkers would be small organisms that gradually fell through the atmosphere, reproducing faster than they sank. Hunters would prey on the other two. It was imaginative, rigorous in its physics, and completely unverified. Sagan's atmospheric ecosystem remains a thought experiment, but it laid the intellectual groundwork for anyone who dares to ask the same question about Neptune. The real value of asking whether Neptune could support life is not in the answer, which is almost certainly no, at least for life as we understand it, but in the exercise. It forces us to think about what life actually needs, what the minimum requirements are, and how flexible biology might be in environments utterly unlike our own. Neptune's atmosphere is a laboratory of extremes, a place where temperatures, pressures, and chemical conditions span a range that encompasses both the familiar and the alien. If we cannot find life there, The question of why not teaches us something about the boundaries of biology. And if, in some impossibly unlikely scenario, we ever did find something alive in the clouds of an ice giant, it would be the most transformative discovery in human history, redefining our understanding of what it means to exist. You let that thought float away from you, as gently as one of Sagan's imaginary floaters drifting through the clouds of a giant planet. The idea of life on Neptune is almost certainly a fantasy, but it is a beautiful one, the kind of thought that softens the edges of sleep and reminds you that the universe is far stranger and more creative than we tend to give it credit for. And now, with the blue giant and all its mysteries still swirling gently behind your eyelids, you arrive at a truth that is both frustrating and quietly heartbreaking. We are probably not going back to Neptune anytime soon. Despite everything we have learned, despite the diamond rain and the impossible winds and the stolen moon and the broken magnetic field and the dark ring arcs and the supersonic oceans buried in the deep interior, Neptune remains one of the least explored major bodies in the solar system. Voyager 2's flyby in 1989 lasted only a matter of hours. One spacecraft, one brief encounter, and then the probe hurtled onward toward interstellar space, leaving Neptune behind in the dark with most of its secrets still intact. In the 37 years since, no other spacecraft has visited. No orbiter has mapped its atmosphere in detail. No probe has dropped into its clouds. No lander has touched Triton's frozen surface. Everything we have learned since 1989 has come from telescopes, and telescopes, no matter how powerful, can only see so much from billions of kilometers away. This is not for lack of wanting. Planetary scientists have been proposing Neptune missions for decades, and the concepts on paper are genuinely thrilling. The most frequently discussed mission architecture is a Neptune orbiter with an atmospheric probe, a spacecraft that would enter orbit around the planet, study it and its moons for years rather than hours, and release a smaller probe to descend into the atmosphere and measure composition, temperature, pressure, and wind speeds directly. Some proposals have included a Triton lander, a small vehicle that would touch down on the moon's nitrogen ice surface and study its geology, search for subsurface activity, and sniff its tenuous atmosphere for clues about its origin and evolution. The science return from such a mission would be incalculable. It would transform our understanding of ice giants the way Cassini transformed our understanding of Saturn's system over its 13 years of operations. Every planetary scientist working on the outer solar system knows this. The problem is not vision. The problem is money, physics, and time. Neptune is staggeringly far away, and getting there takes a long time. Voyager 2 needed 12 years, and that was using a once-in-175 years alignment of the outer planets to slingshot its way through the solar system. A dedicated Neptune mission, launched with current propulsion technology, would take roughly 12 to 15 years to arrive, even with a Jupiter gravity assist. That means a mission launched in 2030 would not reach Neptune until the mid-2040s. The total mission timeline from initial funding to arrival, including design, construction, testing and launch, could easily stretch to 25 or 30 years. This creates a problem for space agencies that operate on political timescales, where budgets are approved and cancelled on 4 or 5 year cycles. Convincing a government to fund a mission whose payoff will not arrive until most of the current lawmakers have retired is a challenge that makes orbital mechanics look simple by comparison. There is, however, a critical window of opportunity that has mission planners watching the calendar with increasing urgency. In the early 2030s, Jupiter will be positioned in a way that allows a spacecraft launched toward Neptune to use a Jupiter gravity assist, dramatically reducing travel time and fuel requirements. This window is narrow, lasting only a few years, and if it is missed, the next comparable opportunity will not arise for over a decade. Researchers still argue about whether this window is realistic given the current state of mission funding and development, but a growing consensus in the planetary science community has identified a Neptune flagship mission as one of the highest priorities for the coming decades. The 2023 Planetary Science Decadal Survey, the influential document that guides NASA's priorities for solar system exploration, ranked a Uranus orbiter and probe as its top flagship mission priority, placing it ahead of a Neptune mission. This was a pragmatic decision. Uranus is closer and therefore cheaper and faster to reach, but it was a disappointment for Neptune advocates who had hoped the ice giant would receive top billing. Still, the Decadal survey acknowledged Neptune as a high-priority target for future exploration, and many scientists view a Uranus mission as a stepping stone that will build the technology and expertise needed for an eventual Neptune campaign. If the Uranus mission succeeds, Neptune's turn will come, eventually. Here is a quirky and somewhat melancholy fact that underscores the timescale of outer solar system exploration. Many of the scientists who first analysed Voyager 2's Neptune data in 1989 were young researchers at the start of their careers. Today they're retired or nearing retirement, and some have passed away. If a Neptune orbiter launched in 2032 and arrived in 2045, a new generation of scientists, people who were not yet born when Voyager 2 flew past Neptune, would be the ones operating the spacecraft and analysing the data. The gap between our first and second visits to Neptune could span an entire human career from beginning to end. This is the reality of deep space exploration. The distances are so vast and the timelines so long that the work is inherently multi-generational. The people who dream the mission are rarely the people who see it fulfilled. You feel the weight of that thought, not as sadness exactly, but as a kind of quiet reverence for the ambition it represents. Somewhere, right now, a graduate student is working on a thesis about Neptune's atmosphere or Triton's surface geology, knowing that the data they are analysing is almost 4 decades old, and that the next dataset may not arrive until they are middle-aged. That is not frustration. That is devotion. And it is the same devotion that has driven every act of exploration in human history, the willingness to begin something you may not live to finish, because the knowing matters more than the timing. And so, at last you arrive at the deepest and perhaps most surprising secret Neptune has been hiding all along. It is not a secret about Neptune itself exactly, but about what Neptune represents. Because as it turns out, Neptune-sized planets are the most common type of planet in the galaxy. Not gas giants like Jupiter, not rocky worlds like Earth, not tiny Mercury-sized pebbles baking close to their stars. The most abundant class of planet orbiting other stars based on data gathered by the Kepler Space Telescope and its successors falls into a size category that astronomers call sub-Neptunes and mini-Neptunes. Worlds roughly 2 to 4 times the diameter of Earth, smaller than Neptune but built from similar ingredients. They're everywhere. Almost every sun-like star in the Milky Way appears to have at least one, and many have several. The galaxy, it turns out, is absolutely lousy with Neptune-like worlds, and our own Neptune is the closest, most accessible example of this dominant planetary type. Understanding it is not just a matter of satisfying curiosity about one blue dot at the edge of our solar system. It is the key to understanding the most common kind of planet in the universe. This realization has fundamentally shifted Neptune's status in the planetary science community. For most of the 20th century, Neptune was an afterthought, the distant, hard-to-reach planet at the back of the solar system that attracted far less attention and funding than the glamorous targets closer in. Mars, with its tantalizing hints of past water, Jupiter with its enormous magnetosphere and volcanic moon Io, Saturn with its spectacular rings. Neptune was interesting but inconvenient, a fascinating world trapped behind a wall of distance and travel time. But the exoplanet revolution changed everything. When Kepler began revealing that Neptune-class planets outnumber all other types in the galaxy, Neptune suddenly became not just interesting but essential. It went from being the neglected sibling at the back of the family photo to the Rosetta Stone for understanding planetary systems across the cosmos. The problem is that we know frustratingly little about what Neptune-class planets actually are. The exoplanet data tells us their sizes and in some cases their masses, but it tells us almost nothing about their interiors, atmospheres, magnetic fields or weather. Are they all gas and ice worlds like Neptune? Or do some of them have rocky surfaces beneath thick atmospheres? Do they all have diamond rain and supersonic oceans and tilted magnetic fields? Do they all have supersonic winds? We cannot answer any of these questions by observing distant exoplanets alone, because the data is too sparse and the planets are too far away. The only way to ground truth our understanding of this planetary class is to study the one example we have in our own backyard, and that example is Neptune. Researchers still argue about the precise boundary between sub-Neptunes and super-Earths, a related category of exoplanet that is smaller and denser and may have rocky surfaces. The dividing line, sometimes called the radius valley, sits at roughly 1.5 to 2 Earth radii, and planets on either side of this boundary appear to have fundamentally different internal structures. Below the valley, planets tend to be dense and rocky. Above it, they tend to be less dense and more gas-rich, more Neptune-like. Understanding what drives this transition, whether it is atmospheric loss due to stellar radiation, differences in formation conditions, or something else entirely, is one of the central questions in exoplanet science today, and the answer almost certainly depends on having a detailed understanding of how real ice giants like Neptune are put together. Here is a quirky irony that ties the whole story together. The James Webb Space Telescope, launched in 2021, is now capable of studying the atmospheres of some exoplanets in unprecedented detail, detecting the chemical signatures of water, methane, carbon dioxide, and other molecules in the air of worlds orbiting distant stars. Some of these exoplanets are Neptune-class worlds, and JWST is beginning to reveal what their atmospheres look like. But interpreting that data requires models, and those models are built on assumptions about how Neptune-sized planets work, assumptions that are largely based on our study of one planet. Our Neptune. The one we visited once for a few hours in 1989 and have been squinting at through telescopes ever since. The entire field of exoplanet atmospheric science for the most common type of planet in the galaxy is resting, to a degree that makes some scientists uncomfortable, on a foundation of knowledge about Neptune that is incomplete at best. It is like trying to write a definitive guide to forests based on a brief walk through a single grove on a cloudy day. This is why the push for return to Neptune is not just about satisfying the curiosity of a few dedicated ice giant enthusiasts. It is about building the foundation for understanding thousands of worlds we can now see but cannot yet comprehend. Every measurement a future Neptune orbiter makes, every atmospheric profile, every magnetic field reading, every observation of Triton's surface will ripple outward through the entire field of planetary science, informing models that are applied to worlds hundreds of light years away. Neptune is the template, the archetype, the one we can actually reach, if we choose to, and study in the kind of detail that transforms guesses into knowledge. You let that settle, the idea that this one blue world at the edge of our solar system holds the key to understanding countless others scattered across the galaxy. Neptune is not the end of the story. It is the beginning of a much larger one. A story about what planets are, how they form, and what they become over billions of years. And you are here, lying in the soft dark, having travelled all the way out to the 8th planet and back, carrying with you the diamond rain and the stolen moon, and the singing winds and the impossible ocean and the broken magnetic field. All of it tucked gently into the folds of your fading awareness. And now the pace slows. The words soften. You've been on a long journey tonight, from the mathematicians' desks of the 1840s to the frontiers of exoplanet science, from Voyager 2's lonely flyby to the geysers of Triton, from the howling equatorial winds to the quiet, crushing dark of Neptune's deepest interior. You have carried a lot. It is time to set it down. Let the facts blur at the edges. Let the numbers dissolve. You do not need to remember any of it right now. The diamond rain will still be falling tomorrow. The winds will still be blowing. Triton will still be spiralling inward, patient as gravity itself, and Neptune will still be turning in the dark, blue and ancient and full of secrets that are not going anywhere. They will wait for you. They have been waiting for 4.5 billion years. They can wait one more night. Your breathing is slow now, deep and even, like the roll of a tide on a shore you cannot see. The blue fades to a deeper blue, and then to something softer, something without a name, and the last thing you're aware of is the faintest shimmer of falling diamonds, catching light that has no source, tumbling silently through an ocean that has no floor, carrying you gently, gently, gently down into sleep, sweet dreams.